Good, energy and work. So when we see this idea of work in physics, sometimes the words don't mean the same thing. If I were to take a book and just hold it here for a long time, I would get really tired eventually. In terms of physics, though, I'm not doing any work. If I'm putting a force on something, it has to be a force through a distance. So just holding something, I'm definitely doing something, but in terms of physics, it's not technically work. It has to be a force through a distance. So we're going to introduce the concept of energy and learn some new problem-solving techniques. In the previous chapter, at the beginning, I said, well, we were talking about forces. Shouldn't it matter the amount of time that a force is applied? And it did, and we had the impulse relationship. In this chapter, if you have a force through a certain distance, shouldn't that matter? It turns out it does. It's something called the work-energy theorem. So we'll see that in this chapter as well. So just like the last chapter had two distinct types of problems, impulse problems and collision problems, this chapter has these work-type problems, and then they have conservation of energy problems. Okay, so this dolphin has a lot of kinetic energy as it leaves the water. At its highest point, its energy is mostly potential. So it's changing forms of energy. It goes from kinetic, the energy of motion, to potential energy, just the energy of position. Now, the lab that we did last week and continuing on to this week, we talked about kinetic energy. So group A didn't really know that much about it until we did the lab. So we'll get into it in more detail in this chapter. Okay, so as this band is stretched, energy is transferred to it through work. And then you can store that energy, and then your child walks through the door. Probably don't shoot him with a slingshot, but maybe like a Nerf gun or something like that. It's made for that reason. So really what you're doing is storing energy for later, and then you let it go. So we'll be able to calculate how much energy is stored in springs or bands like this one, slingshots. So these people are sliding down. They had a lot of potential energy to begin with. It's turning into kinetic energy. And if there's no friction, we could figure out how fast they're going at the bottom. It's kind of like balancing your checkbook. So this picture just shows all different forms of energy. You don't always have to have all of these different forms of energy when you're doing a problem. Mostly we'll have kinetic, gravitational, or spring. In this class, we won't have anything with chemical energy. We might do a little bit with thermal energy in this chapter, and then we'll come back to it when we do thermodynamics. But in this chapter, if you have thermal energy, it's due to work done by friction. So hopefully this won't happen too soon, but if you actually rub your hands together, and then you can feel your face, your hands feel hot. There was friction between your hands. You've rubbed them together. You have turned chemical energy in your muscles into thermal energy, and you can feel it on your face. Okay, so the total energy of a system stays the same. You could change forms, though. So energy of position is kinetic energy. Now, they just use K for kinetic energy in the book. I use KE. The reason is we're going to have something called the spring constant, which is also K, which relates to spring potential energy, so it can get confusing. So when you see when I write it, it'll be KE. Gravitational potential energy is U sub G. If you've had other classes, they might have called it PE for potential. It's the same thing. We just call it U sub G. Elastic or spring potential energy is U sub S. And then again, if there's any work done by friction in this chapter, we'll attribute it to thermal energy. And this stuff is not in this chapter. Nuclear energy actually comes in Physics 221. Okay, so kinetic can change into potential, to chemical pretty easily. It's hard once you get thermal energy to go back the other direction. So these can change direction pretty easily. Thermal energy, not so much. So believe it or not, as I walk across the room, I'm solar powered. Almost everything that we do is solar powered. So how could it be solar powered? I'm using my muscles to propel myself across the room. And the chemical energy in my muscles came from the food that I ate, which was grown in a field from the sun. So nearly everything that we do is really indirectly solar powered. When you drive your gas car home today, it's really indirectly solar powered because the gas came from plants from millions of years ago. So indirectly, your car is solar powered. Unless it's some kind of nuclear power, everything is really, you could trace it back to the sun that we use. You can try it, Rick. Let us know how it goes. Rick said, can we park in those special spots? Yes. As long as you put a note on your car, this car is indirectly solar powered, and then explain why. Okay. Perfect. So this weightlifter is converting chemical energy into gravitational potential energy. In this example over here, we have elastic potential energy of the springboard converted into kinetic energy as the diver leaves the board, and then as the diver goes up, that kinetic energy is turned into potential energy, and then on the way back down, potential back into kinetic energy. And then really what slows the diver down once they hit the water is friction. So you couldn't probably measure it, but the water heats up, the diver heats up as the diver enters the water. Okay, so all these energy transformations going on all the time. Here's a few that we can actually vote on. A child is on a playground swing, motionless at the highest point. What energy transformation takes place as he swings back to the lowest point? So you're on a swing, you go to the highest point, and then as you head from the highest point to the lowest point, what's going on? Okay, very good. It's a voting one. Excellent. All right, good. Excellent. Perfect. Good. We have a gravitational potential energy turning into kinetic energy. Now, a skier is sliding down a gentle slope at a constant speed. Be careful, constant speed is important in this problem. What energy transformation is taking place? Okay, so we're up here, we're heading down here, but we're not speeding up. All right, good. All right. Yeah, it's a tricky one. So gravitational potential energy, right, because we're at a height and then we're getting lower. If there were no friction, that would be turning into kinetic energy. But the kinetic energy is not changing because the speed's not changing. The speed's not changing, so the kinetic energy isn't increasing. So what's going on here? What's going on with that energy? Well, we could attribute it to thermal energy. So the skis probably heat up a little bit. The snow heats up. It might not be very realistic, right? If you're skiing, you're not going to just go down at a constant speed. But if you did, you know, what's going on? It has to be something like that. Okay? All right, good. So energy can be transferred between a system and its environment in something called work. So work is the mechanical transfer of energy. So as I'm walking across the room, that's what's really going on. I'm doing some work and I'm gaining speed. Heat is the non-mechanical transfer, so going from hot to cold, that kind of idea. When we do thermodynamics at the end of the semester, we'll go back to the second case. But work is the way that we can do it now. So this box, I could have a force on this box, and I'm doing some work on it. I'm giving it some kinetic energy. Now, if there's a net amount of work, it'll actually speed up. If I'm just going at a constant speed, I'm doing work this way, friction is slowing it back down. If I did this enough, I could actually feel the bottom of it, and then it would heat up. Okay. So the total energy of a system changes by amount of, the way to read this, I guess, is when you gain kinetic, if you gain kinetic somehow, where do you get it from? Maybe you get it from gravitational, that sort of thing. But if you do have a total change in energy, it had to come from somewhere. And, whoops, did I skip it? And it comes from work. So let me show you a kinematics equation that we had before. It's very, this whole thing that we've done so far is very general. We'll have to get a little bit more specific in a minute. So, back in the first or second week of class, we had this kinematics equation. Now I could multiply, I can multiply the top and or the whole thing through by m over 2. So multiply the left side and the right side by m divided by 2. You'll see why in just a minute. And then I get ma times delta x. Good, so the 2 canceled out on the 2a delta x part. I'm going to put this term over to the left-hand side. And then I'm left with ma times delta x. Well, this is just the net force. It turns out that 1/2 mv squared, that's what we can identify as kinetic energy. That's what this is, mv squared over 2. That's 1/2 mv squared. So this is the final kinetic energy minus the initial kinetic energy. And that's F times delta x. So if it seemed like we should have some kind of displacement component to where the force is applied, it should give us something. It actually does. F times delta x gives us the change in kinetic energy. And that's, in physics terms, the work. Okay, so I'm using big W for work. Because remember, we had weight before. Weight was little w. Here, this is big W. So this has a similar feel to what we did in the previous chapter. We had force times time, giving us a change in momentum. Here we have force with displacement, giving us the change in kinetic energy. So this is the work energy theorem. Okay? It's just a little bit more complicated than that. I just want to show you a picture because we're almost out of time. And then we'll come back to this next time. So I skipped ahead a couple of slides. I just wanted to showing you this picture. It's the parallel part of the force that's lined up with where you're going. So here's some kind of whatever this is. What is this? A dune buggy or something? Some kind of thing on wheels, anyway. And here's a sail. Here's the force on this cart in this direction. Now this force has a parallel part, that's this part, and a perpendicular part, this part. It's the parallel part that actually speeds up this cart. So work is really the parallel part of the force times the displacement. What I just showed you, I just said force times displacement, but really the part that speeds this up is the part that's in the direction that it's actually moving. So it's slightly more complicated, but not too much more. Okay? Good, so that's an introduction to chapter 10, and next Wednesday we'll do it in a lot more detail. So here's what you should do. Group B, I'll see you tomorrow. Everybody else, I'll see you on Wednesday. Well, I'll see everybody on Wednesday, hopefully. We'll finish up homework 5, and then we'll get back into chapter 10 and do a lot more problems and things like that. All right, good. If you don't have lab tomorrow, have a nice fall break. If you do have lab tomorrow, you got to wait another day and then have a nice fall break. Okay, any questions? Excellent, hang in there. I mean, this homework 5 is 5 out of 10 homework assignments. So after this homework set that you finish, the homework for the semester is half over with. Okay.